Hello everyone, this is N. Kavita, working as Assistant Professor in Department of Electronics and Instrumentation Engineering, Hindustan College of Engineering and Technology, Coimbatore. Today we are going to see a topic on LVDT. What is this LVDT? So this LVDT is a linear variable differential transformer. It is an important type of inductive transducer. You might have heard about the word transducer. What is a transducer? So a transducer is a device which is used to convert a non-electrical quantity into an electrical quantity. So such a device is called a transducer. And here, this LVDT is an important type of inductive transducer. In general, the transducers are classified into three types based on your principle of changes: resistive transducer, capacitive transducer, and inductive transducer. Whenever there is a change in the induction, those type of transducer are called inductive transducer. And here we are going to see how this LVDT is being a kind of inductive transducer. LVDT is also called as a position sensor, which is able to convert your linear motions into electrical signal. And in the upcoming slides, we are going to see how this LVDT is sensing the position and how those position is converted into a electrical quantity. We will see the construction of your LVDT initially to get a clear understanding of the working principle. When you look at this diagram, it is very obvious that there are two major windings which are shown here. One is the primary winding and other is the secondary winding. The primary winding is given here in green color. This primary winding is always connected to the AC power supply. Opposite to the primary winding, you'll always have two secondary windings. You can see here, this is the S1, maybe secondary winding 1, and this is the secondary winding 2. And these two secondary windings are connected together. Across these two secondary windings, we will be observing the output. So once it is placed inside the complete former setup, it will be looking like here in your 3D view. You can find at the center there will be a primary winding, on either sides there will be a secondary winding, and here there is an arm, right? So this arm is used to make a displacement. So it is a soft iron core which is made up of a magnet. Along with the soft iron core, you will be having an arm arrangement to make your displacement. So in case of a LVDT, the major input what we are going to apply is only the displacement. And this displacement is going to convert into a differential output. So in the upcoming slides, we are going to see how this LVDT is converting or how it is sensing the position or the displacement into an electrical quantity. For a better understanding, you can see the one more construction diagram. Here we have got a complete former setup which is enclosed here. The complete former setup. Inside that we have a primary winding P, secondary winding S1, secondary winding S2, and there will be a soft iron core. Along with that, we can make a displacement, and that is a movable arm. And now, as we have already had a clear view on the construction, we'll make a quick go on these slides. So we have a primary winding P, we have got secondary winding S1 and S2, and these two windings are placed inside your former. And this primary winding and secondary windings are present at both the ends in a cylindrical former. And both the secondary windings are connected in series with each other, and the primary winding is connected to the AC power supply. The movable part of the LVDT is a separate arm which is made up of a magnetic material. So kindly remember all those construction parts to make you understand the principle of working very easier. We are going to see the working principle of LVDT now. So from the diagram, I'll just give you a quick recap of what is done here again. So assume this is a primary winding and I have placed a mobile core in between AC source. Across the two secondary windings, I'm going to observe what is my output voltage. So at this case, we are going to see the characteristics of LVDT with respect to the position of core. So here the major role is given for the core. Based on the position of the core, we are going to convert the electrical voltage. So the very first case is your core is at null position. Case 2 is when the core is moving towards the left of your null position. And in case 3, your core will move towards the right of your null position. So we will see what is all this about. The initial condition is when your core is at null position. Please do remember the construction what we have seen in the earlier case. So we have got the primary winding, and this primary winding is connected to the AC source, which is always a supply is provided to the primary winding. And at the other ends of the primary winding, we have got secondary windings, which is given as S1 and S2. And these two secondary windings are connected to the series, and throughout that secondary winding, we are going to observe the output voltage. So kindly make a note that whatever the voltage generated by the secondary winding 1, I mention it as E1. In some cases, you can able to see that it is mentioned as either E1, or in some cases it is measured as either ES1. Both are correct. So the voltage which is generated by your secondary winding 1 is termed as E1 or ES1. Whatever the voltage is generated by the secondary winding S2 can be termed as E2 or sometimes as ES2. Make a note of it. So these two secondary windings are connected in series with each other, and it will produce an output called E out. So what is this E out? So whenever these two windings are connected with each other, we'll be identifying only the differential voltage. So E1 minus E2. So the output voltage is obtained by taking a difference in output of the secondary winding S1 and secondary winding S2. And now we'll get back what is the working principle of your LVDT. So now we will see once again like how this is going to work out. So in initial case, whenever the supply is provided to the primary winding, what does it happen? This is a winding, so we will start to find the magnetic flux. It will create a magnetic flux. You know that whenever the current carrying coil is placed or whenever it is given with any AC source or a current, it will start to produce the magnetic flux. And on the either sides, we have got secondary windings. So this flux is going to link with this windings also. And we have got a core in between. It is made up of a magnet, right? So automatically a magnetic flux is induced at this part along with this core. Along with the core, it will produce the magnetic flux for both secondary winding S1 and S2. So here, when your core is at null position, we can able to identify that this magnetic core and this will have an equal flux linkage with the both the windings S1 and S2. So whatever the voltage is produced by S1, the same voltage will be produced by S2 since the flux linkage will be same in case of this null position. So it may be 4 volt or it may be a 4 volt. It will produce equal voltage. So when you take a differential voltage, obviously the output voltage is going to be 0. So please do understand in case 1, when core is at null position, what is happening here is the secondary windings E1 and E2 will be induced with same type of EMF, and hence the output voltage is 0. We'll look into the case 2. So when you go with the case 2, when you are about to move your core to the left of your null position. So let us check. Say for example, the core is moved towards the left side, which means it is getting closer to the secondary winding S1. What happens now? So when the core is moving to the secondary winding S1, what it happens is, as this primary winding is connected to AC power source and this magnetic core is moving towards the left position, more number of flux is started to link along with the secondary winding S1. And we cannot say that there is no flux linkage in S1. Still, the linkage or the air gap between your primary winding and S2 is greater when it is compared with the secondary winding S1. I'll make you clear. So when we are getting into this, P1 is getting the flux linkage to the secondary winding S1 more because the core is getting closer to the left position and the air gap is reduced here. When the core is moving towards the left, the air gap is getting increased to secondary winding. So what happens now is this secondary winding S1 will generate a voltage, that is E1 or E will be always greater than E2. Hope it is clear to you guys. This is your case 2. So when we make a differential output, obviously it will be a positive voltage because E1 is always greater than E2. And this implies that the total output voltage of your LVDT is going to be a positive, or I can say that it is always in phase with the primary voltage, whatever I apply. Let us look on to the case 3. So when you get into case 3, the core is at right of null position. So when a core is at right of a null position, what happens now? So we can see that the core is getting closer to this secondary winding S2, which obviously indicates that the air gap is reduced in this case, and the flux linkage is more with respect to that of the S2. Here the air gap is getting increased, but still I cannot say that there is no flux linkage in the S1. There is a linkage, but it is comparatively less than with that of the S2. So I can say that ES2 is always greater than ES1. Hope these three characteristics are clear to you. And with this characteristics curve, we can able to see that three different conditions are arrived. The condition number 1 is null position. So I can say that is a displacement is 0 or 0 voltage. In case 2, when core is moving towards a left position, I can say that it may be in the positive node, that is E1 is always greater than E2. In case of third condition, when my LVDT is moving towards the right, it is very obvious that E2 will be greater than E1. So from this observation, I can able to arrive a characteristics curve where my displacement may be towards the positive side, that is E1 is greater than E2, or E2 is greater than E1 on the left sides. So whatever may be. So in the LVDT, I can able to convert both the displacements on the left as well as in the right sections. So here you can get into the advantage of your LVDT. It is very clear. It has a very high sensitivity. So based upon the position, low hysteresis loss, low power consumption, fast dynamic response, direct conversion to electrical signals. So it is very obvious based upon the position of the core. Either it may be null, or either it may be left of the null, or it may be to the right of the null positions. Here based on the displacement, whatever I provide, those displacement, based upon those displacement, the output voltage is obtained across my secondary windings. So this is how I can say that LVDT is a kind of displacement sensor or position sensor. Based on the position of the core, the output voltage is obtained, or based upon the displacement, the output voltage is obtained. So what is the major disadvantage of this LVDT? So whenever you have got a stray magnetic field, that is an extra magnetic flux is being induced in the LVDT, the total system is going to get collapsed. So it's an electromagnetic device. So whenever it is affected by any kind of vibrations or temperatures, definitely it is going to affect the performance. So where this LVDT is mostly used? So this LVDT can able to measure your force, your pressure, your weight, and different forms, but it is acting as a secondary transducer. It is the most important thing which you have to take into mind. So we will see in detail about the applications in the later topics. So the main thing is here, the first quantity which is being converted is your displacement. So whatever the main thing is converted first, we call them as primary transducers. So this LVDT is a kind of primary transducer. So we can use in industries to measure your servo mechanisms. It is also used in automation field, turbine, satellite hydraulics, etc. So hope this video is useful to you. Thank you.